Hey everybody, I'm here with another Unity tutorial. This one is about something called normalization. Now, normalization is a very common technique that is used everywhere in video game development, and it's not necessarily something that's obvious or apparent on how to use it, and so thought I would go through a tutorial just explaining what it is and how it's used in game development. And this time I have some slides to assist me and some animation and some demos in Unity. So let's get started. Okay, so let's start by explaining what normalization actually is. So in my mind, normalization is when you are taking a fixed range of values and basically squishing them down into the range of 0 to 1. So these values can be integers or floats or any numbers of that nature, but they're in a specific range. There's a minimum and there's a maximum, and you're taking that range and you're compressing it down to a range of 0 to 1 in floating point number space. So this mapping from the maximum and minimum down to 0 to 1 is usually linear, but it could also be nonlinear. But as I've said, in this case, the minimum value is 0 and the maximum value is 1. So no value will ever go below 0 or above 1. And there's a reason, very good reason for this that we'll get into in a little bit. So you should think of the number 0 as maybe the beginning of the range and 1 as the end of the range. And there is everything in between and nothing outside of the values 0 through 1. So let's take a look at an example. Here I have a range of integers starting at 42 and ending at 176. Now, if you do some simple math, you can figure out that the average value, or the value in between these two numbers, directly between them, is 109. And we can simply do that by adding 42 and 176 and dividing by 2. But what if we were to map that down into a range of 0 to 1? So 42 is the beginning, and 176 is the end, and 109 is directly in the middle, and we map that to 0 to 1, you end up with 0 at the beginning, 1 at the end, and 0.5 directly in the middle. Okay, so let's look at another example. Here we have a different numerical range from -12 to 94, with 41 being directly in the middle. Again, the mapping is exactly the same, 0, 0.5, and 1 for the beginning, middle, and end respectively. One more example. We start with number 1 and as the minimum. The maximum is the number 7. Directly between is number 4. Again, the mapping is still 0 to 1 with 0.5 in the middle. Now, let's say we wanted to find not the middle, but somewhere at 0.1 along the range, between 1 to 7. That number is 1.6. If we wanted a number that was 0.9 in the range, that's 6.4. So how did that work? What just happened there? All right, let's start looking at what that looks like in action. So here I have a simple example in Unity where at the bottom here I have my master slider, which is simply a value that goes from 0 to 1, and it's controlling all of these other sliders. And all of them are set up to go from their minimum values to their maximum values. Minimum to maximum, minimum to maximum. And these are just like in the slides that I showed earlier. And here's another one just as another example. And so you can see that when the slider is at 0, all of these guys are at their minimum values. This is their current value. Current values are set to the minimum value. When I put their value all the way to 1, you'll see all of them have their maximum value. 25, 25, 7, 7, 94. Now, but as I slide this master slider, you can see its percentage is changing. It's value is changing. We go from 1 to 0.9 to 0.8 to 0.7 to 0.6. Notice how all of the sliders are moving in exact proportion, so that as I slide this to higher values, each of these sliders is moving to their maximum value at the same percentage. So it doesn't matter what the range is, the slider will move from the beginning to the end. Obviously, the larger the range, the faster the value will move across. Smaller the range, the slower it goes. But this is basically all that normalization is doing in terms of the numbers that are underneath. To show how the linear mapping of numerical values isn't limited to just strictly just to numbers, it could actually be mapped to something else like colors or angles. I'm showing an example here where the same slider goes from 0 to 1. It will change its value from smoothly between 0 and 1, and this is a linear mapping still. And as I move the slider, you can see each of these color controls has different red, green, and blue values and alpha values, and each of them is linearly scaling from its minimum to its maximum value. So you can see how the colors are changing as I move this slider back and forth. If you look at how this is done, I have these color panels, and each of them has a color start and a color end. So in this case, I'm not using a numerical value at all and letting Unity figure that out for me. I'm just using a simple color, and the numerical values are internally stored by Unity, but I can change the color to anything I'd like. And because I've done that, I have different colors. I even have different alpha values. You can see the alpha for the minimum and maximum color, or the start and end colors are different. And so as I change the slider, you can see the alpha values are changing as well. So you can see this linear mapping between 0 and 1, beginning and end, can have an effect on things like color as well. Let's look at another example. This one is a simple angle control. So I have an arrow that's pointing at a specific angle, and in this case it's the start angle that I've specified over here at 32, and this is in degrees, and the ending angle at 146. And again, by using a normalized value of 0 to 1, we can map that range of 32 to 146 smoothly between the 2 points. If I increase this angle, you can see that it increases the range. And as I decrease the angle, the maximum goes along with it. So now I have a smaller range of motion. So you can see that instead of thinking in this in terms of absolute values of 32 and 104, you can think of it in terms of the beginning of the range and the end of the range. 0 at the beginning and 1 at the end. And just to illustrate what this looks like with a three-dimensional object, we have the same type of range at 42 degrees at the minimum and for 183 degrees at the end of the angle range. And you can see as I move the slider, this object is rotating through that range. And again, all that matters is that we've specified a beginning and end, and this 0 to 1 mapping takes care of how to interpret that. So up until this point, we've been talking about a linear mapping where we have a straight line connecting the minimum and the maximum across the range of 0 to 1. There can also be a nonlinear mapping from the range of 0 to 1. As in the previous graph, the range is a straight line going from minimum to maximum. In nonlinear mapping, the path is not a straight line. This allows you to use mathematical functions that can approximate the results that you're looking for. Or if you'd like to have complete control over the results, you can use Unity's animation curves. I will show examples for this in a little while. In the nonlinear mapping case, the graph might look like this, for example. This is just a simple curve that has a minimum value of 10 and a maximum value, which is just below 20. But as you can see, it's not linear. It goes in a curve, so that 0.8 and say somewhere here, these two values are the same. Before we go further, let's get into a little bit of math as far as Unity is concerned. Unity has several functions in the mathf namespace that are relevant to this tutorial, and so I thought I'd go through them really quickly just to give you an idea of what they can be used for and how they're used. So there is one function that deals with clamping. What we mean by clamping is we are limiting a value between a certain range, between a minimum and a maximum range. In Unity, there's a mathf clamp01 function, which takes a value and basically makes sure that it's in the range of 0 to 1. So, which is relevant to this because a lot of the inputs to math functions are in the range of 0 to 1. If a value is outside of this range, it is clamped to the closest value that's in the range. And so, for example, a value of -1 would get clamped to 0, and a value of 79 would get clamped to 1. If a value is between 0 and 1, nothing will happen to it. So if you want to think of it a different way, it's like taking the maximum of 0 and a value and then taking the minimum of 1 in that value. And that basically keeps it in the range of 0 to 1. Now, the core of all of what we're doing here with, at least in terms of linear mapping between 0 and 1, we're using a concept called Lerp. You might have heard Lerp before, but maybe you're not sure what it means or where it comes from. Lerp is just a combination of two words, linear interpolation. Linear meaning straight line, the numbers go along a line, and interpolation means figuring out values between two other values, between two known values, along a line. So it's just a fancy way of saying, well, I want to figure out a value that is X% between two other values. And this is really great for figuring out a value that you don't know from two values that you do know. And I will explain how that works in a little bit. The next function is the opposite of Lerp, and Unity calls it the inverse Lerp. And this one is very useful for figuring out how far between two values another value is. In other words, what percentage health do I have left? And you will see an example of how this works as well coming up. So let's talk about what Lerp actually does. So in this example, I have a straight line, and of course, like before, it's the x-axis goes from 0 to 1. The y-axis is completely arbitrary, starts at -12 and goes all the way up to 48. So our range here is -12 to 48, just like in one of the examples I showed earlier. So all the values between -12 and 48 follow this line. So we start with -12 and we end with 48. But what if I wanted to figure out what this value is between -12 and 48? Well, I know I want a value that is 0.54 between -12 and 48 because 0.54 is significant in my game. Maybe that's 54% health or 54% of the distance between the 2 points. The 0.54 is a value that I know and that I have specified, but I don't know this value here. I would like to know between -12 and 48, what is this value? So we use the Lerp function. And in this case, we have -12 for the min, 48 for the max, and 0.54 is our interpolant, or the percentage of the way between -12 and 48. The result of this function is 20.4. So 20.4 is about 54% of the way between -12 and 48. And if you look over here, you'll see that's pretty much where we are on the axis. Now, let's talk about going the other direction. In the inverse Lerp case, again, we have a range of -12 to 48, same line, same x-axis, same y-axis values. But this time, we're going to start with the 20.4 value. Let's say I have a value, 20.4, that I know is between -12 and 48, but I don't know what percentage of the way it is between those two values. Let's say I'm trying to figure out what percentage of distance I need to cover based on a 20.4 value that I am passing in. So in other words, again, we're looking for what this value is here on the x-axis. We don't know what that is. Again, Unity has a math function that can help us out. Here, this time we're going to use the inverse Lerp function. And again, the range is -12, 48, but in this case, the value I'm using for the third parameter is a value between these two values. And the answer I'm going to get, this value, is going to be a floating point number in the range of 0 to 1. In other words, between here and here, that will tell me how far between -12 and 48 20.4 is. And the answer in this case is 0.54, just like we got the other way in the linear interpolation function. So what is so special about Lerp and inverse Lerp and normalization, and what does percentage have to do with it? Well, if you think of 0 or 0.0 as 0% and 1.0 as 100%, you kind of know from real world that nothing is really ever below 0%, and things above 100% are usually reserved for sports athletes giving 110% of their effort. But in reality, in terms of games, generally we think of things as between 0% and 100%. So oftentimes you'll have a gameplay mechanic that deals with some kind of percentage. You have X percentage of power you can use, or you have a certain percentage of health you have left. So let's take the health example, and you want to say how much health do I have left. You could show that as 34 of 45 points. You have 45 points total. You currently have 34 points of health. But you could also use this in terms of a percentage. So in code, we're using the inverse Lerp function. We have a minimum health of 0, a maximum health of 45, and we know the character has a health of 34, but we don't know what percentage that is. Inverse Lerp will tell us. The health percent is going to be a value between 0 and 1. And the answer we get is what percentage of the way between 0 and 45 is 34. So we have a simple string that we can construct for the user to say this number between 0 and 1, which again, if you want to get a percentage, you have to multiply by 100 to show it as a percentage, like 100%. And this will tell us the answer to that. If we wanted to go the other direction, we would use Lerp. So if I have a certain number of health points, and for whatever reason I want to express that in terms of percentages, if you step on this item, you will lose 62%. Your health will go down to 62% of its normal value, for example. And so in order to do that, we have a minimum health of 0, a maximum health of 45, just like before. And the percentage of health that we're looking to find out what the value between 0 and 45, that's 62% of the way there, we're using Lerp. And so we have our min health, our max health, and just remember that this value has to be between 0 and 1. So we're going to divide 62 by 100, and we'll get 0.62. And then we construct a simple string that tells you that you have whatever this value is, the answer to this question, that's how many health points you have remaining. So you can think of this as what value is 62% of the way between 0 and 45. Okay, so for this example, I would like to explain what happens when you have a nonlinear mapping of values between 0 and 1. And in this case, I've got an example where I have a red sphere that is being controlled by this slider, which goes from 0 to 1. And just like the linear mapping, 0 is the minimum value and 1 is the maximum value. But the values in between are not linear. They're not smooth, and they're not necessarily in a straight line. And so as I move the slider, the position of this sphere is changing back and forth. It's not necessarily going in one straight line from one minimum to one maximum. And so you can see as I move the slider, the motion of the sphere is pretty erratic. But that's completely on purpose. And let me show how that works. And so again, if you look at the curve, the x-axis goes from 0 to 1, but the y values on the curve can be anything you want. And Unity has a great object called the animation curve, which probably doesn't get too much emphasis, but I wanted to talk about it because it is the perfect way of doing a nonlinear mapping between 0 and 1. So if you look at the example here, I have 3 different curves for the x, y, and z position of this sphere. So as I move the slider, x, y, and z of this sphere is changing according to these curves. X-axis again is from 0 to 1, y-axis is controlled by the curve. So if you look at the sphere, you can see its x, y, and z values are changing from their minimum to their maximum as determined by the curves. And the curves are editable in Unity with a built-in curve editor. So all I had to do was create an animation curve object in my script, this animation curve example script. If you look at the script, you'll see that I've created an animation curve called curve x, curve y, curve z, and it's of type animation curve. And be careful, do not name your class the same as this. I did that as a mistake and I had problems. So make sure you make the class name or the script name different from this name. In any case, I have the x, y, and z curves, and they're editable. So if I click this, it brings up Unity's built-in curve editor, and it has all kinds of curve shapes that I can preset whatever I like. And if I feel like I want to change anything, you can easily manipulate these points and the tangents, move them around. You can also add keys anywhere you'd like. And this is a simple curve editor. And what this is doing is it's taking my 0 to 1 x-axis, saying that this is my minimum value and my maximum value, and arbitrarily laying out what the y-axis should be for every one of these values. And so you're still getting your 0 to 1, and you're still getting a smooth 0 to 1 movement, but the y value, this y value can be anything you want. And so I can move all the way up or down, I can scale this, and you can see I can change the range here. So if I want other values, I can do that as well. And so this lets me specify almost with perfect precision exactly what I would like to see for my y values when I have smooth x value 0 to 1. And if you notice, as I'm doing this, you can see the object is actually moving around because I'm manipulating the curve in real time. So let's just take a closer look at the script for that last example. And I wasn't planning to go into too much code here, but just to illustrate how that works, it's very, very simple. The slider is hooked up to it through a different mechanism, but if you imagine that this main slider value is coming from somewhere else, and that's just a 0 to 1, this t is going to end up being 0 to 1, floating point value. The way this works is these curves, which are editable in the Unity editor, are objects. And if you want to know what value is at a specific x value of the function, which is coming from the slider, t, all you have to do is call evaluate. And so we pass in the same t for each of these curves, and you're going to get, based on the curves, which are different, a different return values. So the x, y, and z values are going to be evaluated separately, and those just get plugged into a vector. So yeah, here I'm just taking the three values from x, y, and z that are coming out of the curve, and I'm using the vector scale function, which is just individually multiplying each of these x, y, z values with a arbitrary vector called scale, which is just a way of deciding how much to multiply each one of these by to scale it up or down, which gives me more control over it, and then I'm just adding that to the original position. Basically, that's how you use animation curves. And even though they're called animation curves, this isn't really necessarily animation at all. This is just simply creating a math function that you can draw with a curve editor. And you can use this for all kinds of things, like how you might want to move a UI object or bounce something, have it like bounce a few times, or have it slide in slowly or leave quickly. You can animate its position based on any curve that you would like. So that's why it's called an animation curve. But again, it can be used for any function evaluation that you like. Okay, so for this example, we're back in Unity, and I'm going to talk quickly about normalizing vectors. Now, I have a separate video that I've done on vectors and vector math, but this is just a bit of a refresher on that and how it applies to normalization in terms of what I've discussed so far about squishing a range of values down between 0 and 1. A unit vector or a normalized vector has a length of 1. And so you can use that aspect of vector length, which again I've discussed in a different video. So you can use a unit vector to get a vector in the same direction of any length. And in this example, I have three vectors. There's a blue one, a green one, and a purple one. So the blue one is a vector that is basically straight up from the position of this object. The green one is a vector that's straight forward from the position of this object. And this magenta one is from the object's position to some arbitrary target. The target is just an empty in Unity, just a transform. And I've arbitrarily put it here, but I can move it anywhere, and you can see the vector will basically follow this object. Now, the reason for this is I have all these different vectors, and they're all different lengths. And these two vectors, the blue and the green, have a fixed distance that's determined by the script that I'm running on this player object called vector norm. And you can see that the forward and the up position vectors are being multiplied by this distance value. And so the distance value is here, and you can see as I change it, these vectors are getting longer. So, but let's see what happens when I normalize all of these vectors. So let's just pick a distance, whatever, and now they're all normalized. And let's switch to wireframe mode so it's easier to see them. And you can see my three vectors are now unit vectors. They're 1 unit long. You can see this square is 1 unit, and the blue, the green, and the magenta are all 1 unit long. So now these vectors are scalable. Before the normalization, they're not really scalable. It's hard to go from a vector that is a certain arbitrary length to another vector in the same direction that's exactly some other arbitrary length. In order to do that, you first have to normalize it, get it to a unit vector. Now it's 1 unit long, and now you can scale it to whatever value you would like to scale it to. So let's say, just to make it easier, I'm going to use the same distance that the target is from the object, from this player object, and I'm going to apply that same distance to all of my vectors. So let's turn that on, and you'll see what happens now is the blue and the green and the magenta are all the same length because they've been scaled, they've been normalized first, and then they've been scaled up to or down to the distance between the player and the target. Now, as I move the target, we'll switch back to shaded. As I move the target, you'll see all the vectors are going to get longer, but they're going to be the exact same length as this magenta one. And so you can see the blue vector going up and the green vector going forward. Their lengths are increasing proportionally to the distance between the object and the target. And if I were to shorten this distance, you can see these vectors are getting smaller and smaller. And so you can see right there, it's kind of hard to get it exactly, but you can see as I get this magenta vector closer and closer, it gets small. These other vectors are getting smaller and smaller. And so oftentimes in game development, you have a single distance, like say the distance from here to the target, and you want to repeat that same distance multiple times, maybe to other targets. Maybe I want to create an effect where this exact distance is the range of my weapon, and I want that same distance to be applied in multiple directions, all emanating from my player object. I can do that by first normalizing, getting a distance, and then multiplying every vector I would like by that same distance after it's been normalized. All right, so that brings us to the end of this tutorial about normalization. If you have questions, please leave them in the comments, and please subscribe if you find these tutorials useful. Thanks.